small enough that...
Well, it's because we're recording,
Oh.
and we want to make sure that the people not in the room and who will look afterwards can hear it. So, welcome everyone to, I guess, the fourth out of 5 seminars this semester in our Beyond Carbon Neutral series. This is the second and final year of a 2-year series that was made possible by a grant that the Energy Institute, along with the School of Environment and Sustainability and Herb Institute for Business Sustainability, received from our Provost and Office of Research as one of the distinguished faculty and staff seminar series. The series is Carbon Mitigation, Moving Beyond Carbon Neutral, looking at negative emissions. A really important aspect of that, of course, has to do with land use. And that's why today I'm very pleased to welcome Dr. Tim Pearson, who is a carbon specialist and the Director of Ecosystem Services at Winrock International. And I know you got some questions up front, but you might want to tell the world here a little bit about Winrock. I certainly, myself in this field, have known of Winrock for many years, an outstanding organization. Tim himself is an outstanding researcher and innovator at Winrock. He's contributed to over 100 climate and land use related projects, leading research and assessment teams, publishing numerous technical reports as well as journal articles. His expertise includes greenhouse gas accounting for land use and looking at it at multiple jurisdictional levels, subnational, national scale, as well as project level, which is, in terms of our Beyond Carbon Neutral, critically important, because to actually accomplish something in the world, you kind of have to do projects, and accounting for land use and the role of carbon at that level can be a tricky business, but thanks to the work of a community of researchers, including those at Winrock and folks like Tim over many years, there's lots of techniques for doing that enable good carbon accounting to come about. And Tim has been a contributor to those efforts, serving on methodology committees for the Climate Action Reserve, the ANSI accredited binational forest carbon standards committee, among many others. So I'd like to very much again welcome Dr. Tim Pearson as our seminar speaker today.
Thank you, John. Very happy to be here. Thank you for inviting me. I'm glad we could make it happen. We've been talking about this for over a year, so we managed to find the time and find the way to make it happen. John asked me to talk about this title specifically, which is, can land management contribute to a net carbon sink, and can it be monitored accurately? It was a little tricky for me to pitch the level and the content of this presentation, so I'm going to give you what I'm giving you, and then I'm very open for discussion and questions about anything else afterwards. So first of all, Winrock International, for those of you who don't know, it is a mission-driven, not-for-profit business. It's a bunch of words. It's committed to innovative ideas, providing technical support, project management. It comes from the Rockefeller family tradition of international philanthropy. Winrock itself comes from Rockefeller, and Win is Winthrop, who was one of the original sons of Rockefeller. And Winthrop was the governor of Arkansas, and he was very much involved in agricultural development in the South. And so the money that came to seed 3 organizations that finally became Winrock International came from Winthrop and from the wider family. Winrock International, broadly, we have a mission to empower the disadvantaged, increase economic opportunity, and sustain natural resources around the globe. Broadly, Winrock as an organization is a development organization. It takes predominantly most of its money from US government and mostly from USAID to have very large projects that run from 3 to 5 years, sometimes more than that in countries around the world, with offices and staff in those countries. Those projects run in agricultural development, in natural resource management, clean energy work, and also in leadership development, civic engagement. My particular part of Winrock is a little bit different to that, in that we're essentially a consultancy and we have a highly technical staff. We're about 15 people, PhD scientists, GIS technicians, and we provide support to countries, to other organizations, to private companies, on subjects that span ecosystem services. So most of our work really has been on greenhouse gases, on accounting greenhouse gases, on working with markets for greenhouse gases, but we also work with water quality and water quantity, biodiversity. So my unit's called the Ecosystem Services Unit. We take science-based approaches for tools, building capacity, methodologies, and we work across a number of different areas, assessing those ecosystem services, working on payment for performance systems, developing tools that really bring the science down to a level whereby it can be used by policymakers, commodity producers. So coming into land use and greenhouse gases, ever since I got into this area, these were the figures that really spoke to me, because they really tell a story, and most of you will have seen this before. But these are the atmospheric measurements of carbon dioxide at the Mauna Loa Observatory in Hawaii. And what really is important to me is that you can see, yes, it's going up steadily through time, but most importantly, you're seeing every single year a cycle of up and down. And let's zoom in here on some of the later years. And what that reflects is the world is mostly covered by water, but the northern hemisphere has far more land than the southern hemisphere. And what you see is the dip in carbon dioxide concentration every single year when the trees flush and come out in the northern hemisphere and photosynthesis increases. So this really tells me and speaks to me how much land use has the opportunity to impact our greenhouse gases. And if we're able to do something more in terms of promoting land use and reducing land use emissions, we really can have an impact on that upward trajectory of greenhouse gases. So this is stuff everyone here definitely knows. Greenhouse gases come about largely now through the burning of fossil fuels that are pulled out of the ground. Those fossil fuels themselves are sequestered carbon from plants that have died and become preserved and transformed in form to coal or gas, oil. So most of the greenhouse gases nowadays are coming from the fossil fuel burning, but there is still a significant amount of greenhouse gases coming from land use change, from cutting down trees, from poorly managing forest. And at the same time, some of those greenhouse gases are being pulled out of the atmosphere as trees grow. So carbon is stored in biomass as it grows. It's stored in the wood in the trees. It's stored in the leaves and branches. It's stored in the root underground. It's also stored in dead wood, which is biomass that's just sitting there and taking time to decompose, and litter taking time to decompose, and that will also decompose to a significant proportion into soil carbon as well. So those are the pools we're talking about really when we're talking about land use storage. And if we talk across the whole of the greenhouse gas sphere, in 2010 there were 49 gigatons of carbon dioxide net emissions. And that's obviously in the transport sector, in electricity and heat production, in buildings and in industry, but there, almost 25% is AFOLU, which is agriculture, forestry, and other land uses. And that's 25% now, but you don't have to go back very far for that number to be very different. Clearly, before we started burning coal, particularly in the 1800s, all the emissions essentially were coming from the land use. They're coming from trees being cut down, being used for energy, being used to produce boats and buildings and everything else. And through time, that land use proportion has grown, but it's grown nothing like as much as the other emissions. So that if we just look from 1750 to 1970, still more than half of the total emissions produced came from the land use sector. If we move that date from 1970 through to 2011, suddenly it's down to a third. Those fossil fuel emissions are huge. So what can we do in the land use sector? Perhaps the most obvious thing is planting trees. We plant trees, they will grow for 10, 20, 30, 50, couple of hundred years, and as they grow, they'll continue to take carbon dioxide and fix it in, particularly into the stem of the trees. And these tree planting projects can be restoring natural forests, as so much of our natural forest has disappeared everywhere around the world. It also can be timber plantations, and it also can be agroforestry, so trees can be used to produce foods, particularly in many developing countries. It's not just trees that sequester carbon. Grasslands can be significant stores of carbon. And that particularly happens in some of these prairie systems where you have massive root systems. And those massive root systems include a lot of fine roots that lead to very high soil carbon stocks in these systems. We also can change the way we manage forests. I don't think any of us, particularly in the development sector, would suggest that we would draw a fence around forests and leave it alone and leave that as a storage of carbon and have full conservation. There are people's lives in and around those forests, and they have the right to use those resources much as we have done in the past in the US and continue to do. And so we can think about how we manage our forests and use the resources in the forest to reduce our greenhouse gas emissions and increase our carbon sequestration. And then the biggest source of greenhouse gas from the land use sector is deforestation. Trees being cut down, particularly across Brazil, the Congo, Indonesia, but all around the world, trees are being cut down, causing massive greenhouse gas emissions. And it also includes agriculture. Of the 24% of the AFOLU, agriculture, forestry, and other land use emissions, approximately half of that, or slightly more now, is coming from agriculture. And that comes from the tillage of soils, leading the carbon that's stored into those soils being released into the atmosphere. It comes from applying fertilizers, and those fertilizers leading to emissions of nitrous oxide, which itself has 300 times the impact per unit of gas as carbon dioxide does. And from livestock, the enteric fermentation from particularly cows, and the manure that's produced from those, these all lead to greenhouse gases. And being mindful in terms of how we manage our agricultural lands gives us potential to reduce greenhouse gases, emissions, increase sequestration, while also supporting our farming communities. So this gives us somewhat of a look at how those emissions are split up and have been split up over the last 40 years amongst this AFOLU sector. So you can see the big portion here is the land use change in forestry, which is predominantly deforestation. But also there's the draining of peat and peat fires, and that's something that's in the news a lot, and a lot of you will see, particularly in Indonesia. We're getting large areas being converted, for example, to palm oil or sometimes to pulp and paper. And as those peats are drained, you're having, there are massive amounts of trees and biomass that's in that peat in an anaerobic condition. As it's drained out, all of that biomass can start to be freed up into the atmosphere. Then we have the enteric fermentation and manure associated with livestock, and then other sectors, rice cultivation, fertilizers that I talked about, crop residues, soil emissions.
What enteric fermentation is?
Enteric fermentation is, particularly within cows in their stomachs, they end up producing an awful lot of methane that comes out either the front end or the back end. And it's a massive source of greenhouse gas emissions and is a particular reason why people try to push away from beef eating. But there are solutions that don't just involve not being involved with cows anymore. But across these 40 years, you can see there isn't a dramatic change in proportion of anything other than we have made progress. The deforested emissions went up for those first 30 years, but we're starting to turn the corner on some of that. But still, it's a massive source of emissions and a massive potential for us to reduce those emissions while also saving the biodiversity associated with the forest, saving the potential that's locked up in the forest in terms of pharmaceuticals and in terms of lives and livelihoods of some of the poorest people in the world who exist in those tropical forests and around those tropical forests. So, how much can be stored? In forests, we can talk about an annual sequestration that could be as much as 12 tons of carbon dioxide per acre per year. The stock after 50 years can span, depending on the forest type, and we're in the world anywhere from 90 to 500 tons of carbon dioxide per acre. And so that's where deforestation is really something we think about. If you cut down a forest, you're releasing a massive amount. If we plant trees, we're gaining a small amount per year, but that gain continues forever. And then we have all of the other ancillary benefits that happen from us having forests. And similar numbers can exist for grassland. And what does it mean? Many of you will know this. A ton of carbon dioxide is approximately the emissions from a family car every 2.5 months. Household use of heating, cooking fuel every 4 months. Good deal less in Hawaii and a bit more in Maine. Your household use of electricity every 6 weeks or so, and your refrigerator's electricity use every 15 months. What is the actual offsetting potential if we do look at the land use sector? So of those 49 gigatons of CO2 that are emitted per year currently by estimates, if we look at something where we're paying just $20 per ton of carbon dioxide, then there's something like 3% of that could be offset in the agriculture sector and 3% in the forestry sector. So as much as 6% could reasonably be offset at $20 per ton, which is not an excessive price. If we're able to go as high as $100 per ton, then as much as 15% could be offset. And so what's the history of climate change mitigation? A lot of this started in 1992 with the Earth Summit in Rio, which led to the formation of the United Nations Framework Convention on Climate Change, which is when the world first started to come together and see this could be a problem and it's something we have to do something about. The Earth Summit moved on to the Kyoto Protocol, which was signed initially in 1997 and entered in force finally when there were enough ratified signatures in 2005. Kyoto Protocol was the aim that all the developed countries would come together and do something about their emissions. They focused on a 1990 reference period, and they were going to try and reduce emissions relative to that. It did not involve developing countries having their own targets to reduce emissions. It really was developed country focused, and it was significantly holed when the US pulled out at about this point. But the CDM, which is the Clean Development Mechanism, was a system by which those developed countries could invest in actual projects happening in developing countries and claim those emission reductions and use those to meet some of their own targets. And the CDM, while it was being successful, it had almost 8,000 registered projects and 1.9 billion emission reductions issued. The whole Kyoto Protocol really has foundered largely because lack of political will and political support and not enough pressure put on those targets, because there has to be that demand driving a market mechanism to try and reduce those emission reductions. Largely, the voluntary market stepped in as a means by which emission reductions could still happen. But the voluntary market necessarily is limited, and some of that limitation comes about because who's going to pay? It's coming about through people making philanthropic efforts or efforts for public relations, and that necessarily is going to be somewhat limited. So you can see over the entire period of life of the voluntary market between 2005 and 2016, there were just 1 gigaton of carbon dioxide sequestered, and that's less than 2%, of our annual emissions of greenhouse gases. So the voluntary market isn't going to cut it. We have to find some reason to push people to have to reduce their emissions, not to solely want to reduce their emissions.
I'm having a hard time with the unit. Is that a gigaton of carbon or a gigaton of CO2?
It's a gigaton of CO2, so
Okay.
1,000 million tons.
Gotcha. Well, sometimes the currency is carbon and sometimes it's
Yeah.
CO2.
No, I'm trying to operate in carbon dioxide because
Okay,
it
thanks.
is. We operate also in biomass, carbon, and carbon dioxide. So
Yeah.
biomass is twice carbon, and carbon dioxide is 3.7 times carbon.
Right.
So carbon dioxide is what the international world operates in predominantly, even, and so we'll try and stick there.
Okay, thanks.
More recently, the REDD+ mechanism has come into existence. This is reducing emissions from deforestation and forest degradation, and then a plus, which includes fostering conservation, sustainable management of forests, and enhancement of forest carbon stocks. This really was developing countries wanting to be involved in the solution to climate change, wanting to have the opportunity to receive finances to protect their forests, to have forest protection be a land use planning option within these countries. And so REDD+ exists. it has been being developed for many years, and most forested developing countries are on somewhere on the scope of developing their systems, coming up with a reference level of how many emissions happen per year from deforestation and degradation, registering with bilateral agreements with leading countries such as Norway and Germany and the UK, or with multilaterals led particularly by the World Bank, to try and receive payment for those emission reductions. But the demand is still there, and so there really isn't the kickoff to try and make this into a massive scheme because the finances aren't there yet. The world has continued moving forward, and as you will all know, the Paris Agreement was signed in 2015, and this was the post-Kyoto attempt to do something. There were 195 signatories with the full intention of keeping climate change, global warming to less than 2 degrees Celsius, and seeking to keep that much closer to 1.5 degrees Celsius. Each country then had a nationally determined contribution which said, this is what we are going to do to reduce our emissions. And again, at some point in time they would say, we're going to reduce our emissions by X percent. In terms of developing countries, they'd say, we're going to do this X percent on our own efforts. And then we're also going to offer X percent as a conditional, meaning if your more developed countries are willing to invest, then we're going to go further. And there's still an awful lot of negotiation, discussion on Paris Agreement and nationally determined contributions and the development of market mechanisms. But the hopeful side, at least, is this is the direction we're positively moving in as a world to try and tackle increases in carbon dioxide. And some of this can be witnessed in terms of some of these carbon tax schemes that are existing in different countries. So these are multiplying relatively rapidly, and not just in developed countries. For example, Colombia has its own carbon tax now, and Chile. And these carbon taxes are really a means to bring the population into reducing their emissions and having a design of a national system that is going to focus on carbon as an important commodity and greenhouse gases associated. And then when you have these sort of systems with carbon taxes, then the governments can choose the way they funnel the money coming out of that. And so Australia is a good example of a country, and Colombia will be, where those carbon taxes are then diverted to national systems, national markets, where there are projects that reduce greenhouse gases, and the carbon taxes can be a source of financing for them.
Are there, just a quick question, are there any of those that are where any carbon tax is specifically hypothecated towards land use mitigation?
So Australia is a good example where they have a carbon tax, or have had a carbon tax. Again, it's politically complicated there. Yeah. And they do have land use projects, and those land use projects are tree planting, forest protection, protecting the bushland in Australia, and they have auctions by which project developers can come in and offer a certain number of greenhouse gases at a certain price, and the government commits to pay for them.
So what's the big jump in 2005? The EU or something comes in? What's that one?
That must be, is that Finland?
That must be EU.
EU, oh, EU ETS, yes, it has to be. Has to be. ETS.
Yeah, there's a lot of shades of red there, so.
Yeah, it's maybe not the best. Yeah, exactly. So the 2005, remember, that was when the Kyoto Protocol came into effect. And so the ETS, Europe decided to manage all of its greenhouse gases through the EU ETS, and so that led to immediate impact there.
Tim, can I ask, with China, for the last 2 years, what policy development is responsible for those big blue bars that look like China? The light blue bars?
So this one is going to be California, right?
At the very end.
Oh, at the very end. Yeah, I think they're postulated, right? I think those haven't happened, but I think this figure comes from 2016. But
China has proposed moving towards a cap and trade type system for some of their emissions. So it's not implemented, but it's in process.
Yeah, and some of those are some of the most interesting movements. China and India being these countries that have really come up to to rival and exceed the US in terms of their emissions, do have an interest in turning this around. And China, as everyone saw from the Olympics and other places, they really are suffering from some of these environmental effects. It isn't necessarily greenhouse gases in every context. It's burning a lot of fossil fuels, a lot of coal, and having very bad air quality. But it's all associated, and countries around the world are aware they have to do something. So that's the positive
So
side.
it looks like there are only 3 American states: Massachusetts, Washington, and California. Maybe Oregon should be up there.
All of these are in, I think if we were to go further into the future, we would start to see more. California really was a leader. Washington, Oregon, Colorado.
Wasn't
some of
there
these
something
others.
in New England, I think?
The RGGI is the Regional
there's
Greenhouse Gas
Massachusetts up there.
Initiative.
Oh.
And so that's across, and all the way down to Maryland.
Right.
That was solely focused on power generation.
Ah.
And for a long time their cap was way too high, so they weren't really reducing any emissions. But RGGI, not entirely my specialty, but is supposed to be coming up again, and I think it's going to make a renewed push. Okay, so that's the background, and if we're going to turn to looking at how can we measure forest and agriculture, we can have all the best aims in the world, but unless we're able to use the science to actually say, this is what was emitted, this is what would be emitted, or this is what will be sequestered, all of that is meaningless. We have to have science-based numbers that then can allow a market-based mechanism to promote positive practices. And traditionally, we've used ground measurement. And this is based on long-standing forestry expertise. If you were to actually want to know the amount of carbon that was in a tree, you'd have to cut down that tree and dry it and weigh it and do some chemical testing. And then once you've done that, you would not have a living tree anymore. So it's absolutely impossible to actually go through and completely measure your carbon in trees. But instead we have forestry expertise, which creates these allometric relationships. So from easily obtained measurements of forest, we're able to come at an estimate of the biomass of the trees. And from the biomass, we have a relationship that approximately 50% of the biomass of the tree is actually, the dry biomass of the tree is actually carbon. And so we have allometric relationships like this. So a diameter at breast height, for example, is measured, and from that we can estimate the biomass of the tree. Sometimes it's diameter and plus wood density, sometimes diameter plus wood density plus height. But we have these relationships that allows people to go out into the forest, measure a bunch of trees, and have an estimate of the biomass. Equally, below ground biomass is even more challenging. It's an awful lot of work if you want to try and dig up trees and work out how much biomass is in those roots. Instead, we rely on the literature and on research that's been done that allows us to create somewhat of a stable relationship between the above ground biomass we've estimated and the below ground biomass we want to estimate. Again, we can't go out there and measure everything, so the basis of what we do is sampling. We measure a subset in order to estimate the total. And the pools exactly aren't just the live tree. We'll also measure down dead wood. This will often be in line transects, where we'll measure the places where the wood's crossing, and then we'll have this in separate classes of decomposition of the wood. We'll have clip plots that will look at litter or herbaceous vegetation. We'll take soil carbon through having cores and augers, and then analyzing the bulk density of that soil, and then the percent carbon of the soil. And together that gives us an estimate of the soil carbon. As I said, we can only sample a subset, so we're getting into some of the statistics we have to think about. Accuracy and precision. We can be accurate but still have a huge range of data. So if we went out there and we measured 5 different plots and the average was 100, but the numbers span from 20 through to 550, yes, we have an idea of where that mean value is, but we're imprecise. We have a wide range, and so we can't be that confident in the final number. Equally, the worst case is where we're highly precise, we're very tight on the numbers that we're coming up with, but we're wrong, we're inaccurate. So we chase always this system where we're both accurate and precise. Accuracy is dependent really on the science that's initially coming into your monitoring program, making sure you have those good relationships in terms of allometry and in terms of factors and standards. And then the precision often comes down to the number of plots you install. So these two figures at the bottom come from a project we had in Bolivia where I think 600 plots or so, this was early on, this was in the late 90s, 600 plots or so were measured with the idea we're just going to put a lot of money in and we're going to get the best answer possible. And it's very enlightening really to see that the number of plots to get a fairly low level of precision is very, very low. And the more precise you want to get, you're getting an exponential relationship in terms of what you're trying to achieve. And on the other side, the costs also have some of that same relationship. You'll have a fixed cost that's associated with training up your crew, having all the equipment necessary, sending them out in the field, and then the relative cost of doing 80 plots versus 4 plots is not that massive. It's only when you start to come up towards 600 plots that it's a significant amount on top of that. But you can still see the fixed costs are an important part of that. And that's the consideration when you come into any of these monitoring planning. So ground measurement, that's what we've traditionally done. That's the basis for most of the projects that exist around the world right now. We have the potential for high accuracy and precision. If we go out there, we have good methods, we put in a lot of plots. But there are weaknesses. We can have very high costs, particularly when we're looking across a large area or in a very variable system, then you're going to need an awful lot of plots, and you're going to need a lot of laboratory work as well. And you're dealing in some tropical forest areas, the accessibility is really, really tough, which pushes the cost massively. Crews might have to hike for a day and a half just to reach one plot, and it becomes untenable, really. So we look at newer ways to try and think about this, and we'd immediately fall down on, well, remote sensing. That should be a way we can analyze. It certainly solves the problems of access. Remote sensing allows you to get very rapidly anywhere, whether that's putting a system on top of a plane or taking satellite data. Access largely disappears. And cost, it can certainly decrease compared to fielding a team. It depends on the system, how complex the system is, and how complex your equipment is. So remote sensing is essential for determining areas associated with changes in land cover. So even if we're operating in the ground-based estimation of carbon stocks, we still need to use satellite data to record this is the area of forest in 2005, this is the area of forest today, and the difference between the two is the deforestation we've recorded. But satellites themselves can't directly measure stored carbon. Satellites are picking up some sort of reflectance of data, whether that's visual data, radar, microwave, laser, something. They're picking up a response from something on the ground, and that response can't be, this is 20 tons of carbon. What they can do is they can measure relative greenness. They can measure heat spots, so they can start to look at where fires have existed. There are even satellites that are able to look at the carbon dioxide flux. So that's saying in a given year we can be somewhat confident this is the emission that happened. But a tree, as we know, can grow for 500 or 1,000 years, and so that is an awful lot of flux that comes about to develop whatever stock is there. And remote sensing exists across a broad spectrum. We can go from 500-meter resolution all the way down to 60 centimeters or even less than that. And that really has implications, both in terms of the processing cost. You can have one scene of MODIS at 500 meters, but to get the same area covered in a high resolution, you're going to need probably thousands of scenes, each with their own processing time and their processing costs. If you're dealing at 500-meter resolution, you're probably only going to pick up big areas that are deforested. Something that's 100 meters or more being deforested is going to show up in MODIS. Most common is something like Landsat. That's about 30-meter resolution, and that's freely available now. Didn't used to be as freely available. Landsat is most commonly used for looking at deforestation. It can pick up anything as small as roads, but Landsat is too broad a resolution to be looking at the loss of individual trees or even very small clumps of trees. So here's an example. This is from Cambodia. This is a Landsat analysis looking at deforestation. This is a deforestation frontier. So you can see between 2000 and 2001, here's the black area. The red area, 2001, 2006, and 2005. 2005, 2007 is the purple area. So you can see the deforestation expanding out there. That's our activity data. That's what's happened. And then we need the numbers to put to that to say what the greenhouse gas is. So what's the emission factor to apply to that? This is Ghana, another example of work we've done fairly recently. You can see Ghana is an interesting country. It has a humid area in the southwest there, and the further you go up towards the Sahel and towards the Sahara, you get more open, more dry forest. So you can see there's areas of forest loss, again, in different time periods, spreading out. So we have a highly mosaicked environment, unfortunately, now in Ghana's remaining forests. And deforestation even happening up into the dry forests. And then we look at the fires, and the fires really are happening in those very dry areas. And you can see some of those pixels are burned as many as 3 times within this, this 15-year period in some of those dry areas. And so satellites are very good at doing this sort of thing, of picking up where deforestation's happened and where fires have happened. But the limitations of spectral imagery, of visual imagery, they can't penetrate the canopy. So very quickly, the canopy is exhausted. When you grow trees, the canopy closes and shows up in imagery as closed canopy. And that could be a forest that's 10 years old or a forest that is untouched. It could be a forest that has a stock of 50 tons of carbon, or a forest that has a stock of 500 tons of carbon. And there's cloud cover that can't be penetrated by the spectral imagery. So in many of these humid areas that have the highest stocks, they'll have cloud cover for most of the year, and suddenly that spectral satellite is not useful. So alternatives that can penetrate the canopy and can penetrate ground cover include radar, or I'm going to particularly focus today on LiDAR, which is light detection and ranging. Essentially, it's a pulse laser. The laser is fired down, usually from a plane firing overhead, and the laser pulses are able to penetrate through the canopy and produce basically a picture of what's there, hitting the ground with some of the pulses, hitting sub-canopy layers and the top canopy. So that's what you can see. This laser coming over, it's going to pick, is it just low vegetation? Is it high vegetation? And then even if it is a high vegetation, are there the multiple layers that exist there? But all the LiDAR is telling you there is what canopy exists and how high is the canopy. That, again, isn't giving us carbon. And so there are other relationships we can start to think of and start to create that allow us to extrapolate from that LiDAR imagery to a carbon stock, looking at the height of the trees, looking at the relative density of the trees. And that allows us to create these relationships between the biomass and some of these factors measured. And this is a study which will be submitted pretty soon for Kalimantan in Indonesia. And you can see the relationship is pretty good between field measured biomass and measurements of biomass coming from the LiDAR imagery. And then you can extrapolate out from that, creating new relationships, pulling in information, socioeconomic information, and Landsat, or broader spectrum satellite data related to that LiDAR data. And then we can start to create some of these carbon stock maps that will let us know what exists across the whole of Kalimantan. So you can see the coastal areas really are heavily degraded, and when you get up into the highlands, you have higher stocks still. And then you can start to look at the forest degradation. What areas are most reduced in stocks compared to what they would be if they were untouched? And forest degradation is something I want to talk about. All the numbers that we saw out there for AFOLU and for land use really were focused almost entirely on deforestation, because forest degradation is the thing that we don't know very much about, largely because of a lot of these issues we're talking about. Forest degradation can't be picked up very easily by satellite data. Forest degradation is something going from 80% crown cover to 50% crown cover, or 90% crown cover to 60% crown cover. These things that aren't going to show up very easily in moderate resolution data. So this is a paper we put out last year that started to put numbers on that for the first time. So of the annual emissions we calculated of 6.2 gigatons from deforestation, we were estimating 2.06 gigatons from degradation. So 1 in 4 of emissions from combined deforestation and degradation is actually degradation and is currently not really being counted. And you can look at that, breaking it up. Most of that comes from timber harvesting and the emissions associated with timber harvesting across the tropics. also emissions happening from unsustainable use of wood fuels and from anthropogenic fires. And you can see within individual countries, the proportion can be very high. Some of these, Burkina Faso and Sudan, all of their emissions are actually degradation, not a mix of deforestation and degradation, down to, on this end, your Nicaragua or Uruguay, that it's almost all deforestation. But it's an important missed element that's missed partly because we don't have the tools to be able to capture it.
Just a
Yes.
question on that. The timber, you're counting that as an emission, but does some or much of that go into a, built environment stock of some kind? I mean, is it, or is that?
Yeah, absolutely. It's complex. Most tropical timber harvest is on a selective basis. Not all of those trees have a lot of value. Some proportion of the trees have value. So they'll go in and they'll take out 1 tree a hectare or 2 trees a hectare or 5 trees a hectare sometimes. But mostly down at the lower end, to get those trees out, they'll put in roads. And then they'll put in skid trails that drag those trees out of the forest. So all of those are pretty much committed emissions. This is the infrastructure that has to go in. And then when you cut a tree down, the tree is felled, it's cut, and the log is extracted out of the forest. But about 50% of the biomass of that tree is actually the stump and the top of the tree, which is just left to decompose in the forest. When a tree falls down, it actually causes lots of damage to the surrounding trees. Smaller trees get snapped, uprooted, killed. So there's emissions that happen in the forest there as well. Then you get the tree out of the forest and you bring it to a mill, and approximately, in most cases, 50% of the biomass of the tree is lost in wood waste almost immediately, and very little use in many of these countries of biofuels at this point. So that's an immediate loss in terms of the sawdust. And then it goes into in-use in products, and you get what you'd expect, the exponential decay curve of its in-use products. So a lot of the products are retired within the first 5 or 10 years, and then they're either burnt or they're put on a refuse pile and they'll go up into the atmosphere. And then some proportion, I think maybe 10%, I think it is, of the product that was created is in a long-term storage that goes over multiple decades. But it is a complicated system. It really depends on the country. When you start talking about a more developed situation, which is happening in countries all around the world, and you have landfill, then some of that wood is stuck in the landfill, and that's an anaerobic condition, and it can remain sequestered, the entirety of that product. But if you have a refuse pile or you burn it, then that's going up. So this is...
Maybe you answered this earlier, but the United States and Canada are not included because?
They're not good in this case because we really are looking at developing countries in this particular case. We could do something for, we have looked at things for the US, but this is under the context of the RED Plus, which I was talking about before, the reducing emissions from deforestation, degradation, which is focused on those developing countries. And the deforestation is the headline, it's what everyone talks about, but some of the standards now say you have to also think about degradation. And if degradation is more than 10% of your emissions, you have to put in place systems to assess it. They want to avoid the situation where there is some sort of leakage going from deforestation to degradation, where you're creating this loophole where countries are just going to reduce the stocking of their forests to save themselves from the deforestation and get paid for the full saving of deforestation. So that was the nexus of this paper, really. And you can see this is another figure from the paper where you look at the total degradation emissions. These are by subnational administration units within these countries, and as a proportion of deforestation emissions. So some of this is scale dependent. So across Brazil, for example, you have massive states, and so their emissions are going to look bigger. But you do get to see some really interesting patterns. For example, the fuel wood emissions happening here in East Africa and in South Asia, or fire emissions happening here in the Congo. You can really see the big timber production areas in Indonesia and Brazil. So if we were to look at for something like the timber emissions, given that we identified that was the most important, my paper from 2014 detailed the ground-based method by which we'd do that, which would be we'd go out into the forest, we'd visit a set of those timber harvesting gaps, and in those gaps we'd measure the dimensions of the remaining stump, and we'd measure the dimensions of the top of the tree, and we'd measure the distance between the two, and from that we'd get an estimate of the volume of that tree. We'd then be able to use the allometry relationships to go from our measurements to what the biomass of the total tree would have been, and that allows us to work out the waste, and the emission will happen in the near term from the stump and from the top. And then we can go around the gap and measure all those trees that are snapped or that are uprooted and bring in those emissions here. You can see gaps can be an absolute mess depending on how it's measured. And then here's what we're talking about with the skid trails. You know, often there'll be bulldozers, sometimes there'll be skidders. Those can cause emissions, and the roads in particular can cause massive emissions, and that's an area of deforestation that's across that area. The skid trails is less so because I don't think the bulldozers really want to drive into a big tree, even if they physically could. So we really are talking about smaller trees, but there's still an emission. So that requires a fairly significant amount of groundwork. And then what you have is an emission factor that says per cubic meter, say, of timber that's extracted, this is the greenhouse gas emission that results. We have to apply that to something. And we could apply that to statistics that are produced by logging companies or by governments and come up with an estimate of emissions. And that's what we've done with Ghana and Guyana and many countries around the world. But that's subject to criticism. How good are those numbers? We often don't know the degree by which those numbers are accurate, either in terms of the reporting of the logging companies to the government or the government's ability to have a complete reporting. It also in no way would capture illegal logging, which in many cases is considered to be as much as 40% or more of legal logging. So we started to look at a satellite-based approach to try and think about those emissions. And this is also in Indonesia. We took a plane and flew over a set of concessions and had complete coverage of those. And you can see skid trails particularly are a really interesting case. So this is the LiDAR data. You can see that laser is coming in and it's capturing its responses from all these different height points. So for example, on a road, that's completely cleared. So it's not picking up anything until it hits the ground there. If you're in the unaffected forest, it picks up this diverse canopies, right, that exist there. The skid trail is something that's interesting because the skid trail is just a path that's cut through the forest, and often that won't impact the canopy at all. So what you're doing is you're actually producing some sort of tunnel through the forest. If we're looking at spectral imagery, there's no way it would be able to capture that. But LiDAR does. It gives us that ability to say, hang on, there's this gap in terms of the density of responses happening in this area. So here's some examples of some skid trails. You can kind of see there's one here. You can see through to the ground. But here, there's no way you'd know it was there. And so what we were able to do, working with a partner organization on the remote sensing, is create this system that's automated, that allows the processing of that LiDAR data. And from that, they're able to separate out, well, here are the roads, here are the skid trails, and here are where the gaps exist. And then we paired that with our ground data to allow a measurement of a given area of road or a given area of skid or a given area of gap to be equated to an emission and to an estimate of the volume that's taken out. And we take that a step further because there's significant cost. LiDAR requires you to have all sorts of permissions for a start and then also pay for a plane to go up there and spend the time. So we also created a relationship in it's a paper that's currently being submitted that then creates a correlation with the total emissions with the road emissions or the length of road, because we can, as we said, we can pick up those roads from those moderate free remote sensing imagery, the Landsat and others. So we're able to use this better, more complex, more detailed imagery to give ourselves new tools that allow us to do deeper analyses. And tools is another thing I want to talk about. My team has for a long time now been working on developing tools that allow non-expert users to come in and try and understand some of the science and ask their own questions. It really is a moving field because big data is something that's just growing and growing, and the availability of these big data sources is something that's a capability now that didn't exist 5, 10 years ago. And so we can bring some of these data and process it and put it in a form that can be used. One of the earlier tools we developed was for the United States Agency for International Development that allowed them to put in very simple factors and therefore come up with an emission of their impact on greenhouse gases from the land use sector. They invest an awful lot of money, and at one point all they were saying was, we invested money across X hectares, and that wasn't giving them any information in terms of greenhouse gases. So that was a tool we created. And we moved on to many other things, and I'm just going to highlight a couple of them. One of them is the Watershed Ecosystem Service Tool, which is something we created in Cambodia. It's a web-based interactive planning tool. The design of it was to allow local governments across Cambodia who have this requirement to plan for the future in terms of their water use and their canopy covers, to see what the implications are of some of those plans and put it together and have a decision-making that's thoroughly informed, that's science-based, it's objective. It gives them something that's highly accessible. It's basically a GIS tool, but they don't need GIS skills to use it. It has extensive data underneath it. And so this is what it looks like when you first come in. It really basically is online GIS, but you don't need to know the GIS. You can turn on and off all of these layers, and you can look within each of these different categories. So for example, that was the land cover, the sediment erosion. This is percent change in rainfall that's expected by applying climate models to those data. And then the vulnerability to climate change across those different areas. So you can look, I believe this area here is a rubber plantation, and we can show that it's highly vulnerable to climate change, and so it's something you need to know. I think there are some oil palm plantations here that are also highly vulnerable. So it allows someone without any of that knowledge and expertise to be able to ask a bunch of these questions and start to get some answers. So within the tool, they can identify a particular area. They can click and pull out a polygon of where they want to focus, or they can choose an administrative unit and focus just on that. And here's some of the data that's underneath and that's come out from working with this. You can look at, as deforestation increases, what is the impact then going to be on the aquifer recharge and therefore the water availability for the farms and for the communities afterwards. Higher deforestation is going to lead to less of this water reaching down to the storage there. Nitrate loss also picking up as deforestation happens. A sediment loss radically increasing as deforestation happens. And so for your given parcel that you choose and you want to look at, you can get some of these specific answers. You've identified 100 hectares or something like that, and then it'll say, here's your sediment loss based on these different land uses you've chosen. Here's your water recharge. Here's your nitrate. And what makes the tools like this is unique is it integrates the assessment of those ecosystem services, of greenhouse gases, of water quantity and water quality with climate change. It allows this variation of scales from down to a small farm all the way up to the whole country, allowing this integrated planning across the lot. It's online, it's interactive, it's accessible, and it's usable. And it really pulls some of this data into a position where it can be used, and it's not just stuck requiring high-priced consultants to come in and do the work for them. Second tool I'm going to talk about is the Croatia Counter, which is something we produced for the Croatia organization, which is across Asia supporting commodity producers. And they wanted some way of knowing what are the greenhouse gases associated with their agricultural practices and what would happen if they changed their practices. So traditional key performance indicators can be time-consuming, they can be expensive, and they are very difficult to compare against if different people are using different methods in every different context. Use a tool like this and it can be fast, it can be free, it can be objective, and it can be comparable. So you run through the tool, for example, and you'd select your region, your country, and the region within your country. You select your crop, the area of cultivation, and the yield you expect from that crop. into some simple data on fertilizer usage, some agrochemicals, some of your practices, and also some of your fossil fuel use. And then you calculate. And for example, here you can see 100 hectares, for example, of cacao, of cocoa, in Indonesia, in Aceh province. And what you see is you're putting in a cocoa plantation, you're going to actually get quite a lot of sequestration. You're growing trees there. You're going to get some emissions because you're applying some nitrogen and some urea. And then you can express those numbers either as the total emissions, tons of carbon dioxide, or you can express it per yield. Commodity producers typically don't want to reduce their emissions by reducing their production. That runs contrary to their own business. But if you look at it on an intensity basis, how many emissions are we getting per unit of cocoa produced, then that's a positive way to make a contribution without affecting a bottom line.
The savings from putting in the cacao plants, whatever, is quite dramatic. But doesn't it take a while for those plants to grow?
Yeah, I mean that's not this year. So this is an annual. In this case, it's an annual sequestration across 100 hectares. So you're getting. It's 2,000 tons across 100 hectares. So it's a fairly small amount per hectare, but some of these are large scale in terms of commodity production. And then you can go in this tool and you can say, what if we did something different? What if instead of synthetic fertilizers, we started to apply some manure? It allows the comparison. Suddenly you're applying manure, and what happens is you're directly applying carbon to your soils, so you're actually getting some sequestration in your soils. And so you get to ask, introducing these alternative practices, what's that going to do to my emissions? Again, totals and per yields. And that was that.
So just on that last slide again, where you applied the manure as the treatment, and you got some soil sequestration. Did you get? I guess is that a small amount of N2O then that is showing up there?
Yeah, exactly here. Getting some emission that
but that's
happens.
still small based on. Is that based on some fairly general factor, or
these are based on IPCC approaches in this case. So there are always going to be some weaknesses, but it's the first approach.
Yep.
Not everything is IPCC, in that we have much better data, for example, on some of the the tree sequestration rates. But a number of these factors that are what's the nitrate emission from applying a certain fertilizer, we have to go with those generalized numbers, and it gives you at least a very good first estimate.
So this is maybe completely off the wall, but I'm remembering your very first slide where you showed the annual fluctuation in parts per million for Monolo, which I didn't know anything about until today. It was about 8 or 9 parts per million per year based on when the trees are in foliage and the trees are cropped. This seems to be the most difficult category to quantify. It's just so you've explained how complicated this is. But the other sectors, it's a lot, presumably it's a lot easier to figure out the amount of carbon being produced or CO2, whatever metric you want, per year. It seems like between adding up those other precise numbers and looking at the annual seasonal change, that you might be able to back out a really gross figure of what's happening with land use. You follow me?
Yeah. The problem with that is there's the ocean sink. Some proportion of carbon dioxide every year disappears into the ocean, and it's actually slowly acidifying the ocean, which you will have heard of. And so you're absolutely right. In theory, you could deduce, but the ocean sink is not constant and is not really known. So that really adds this extra element that screws us up, kind of.
So there's another element that you touched on briefly that's really a thorny problem, and that's soils, because in some systems, in many systems, there's more carbon in soils than in trees. And we have the problem that you can allometrically measure tree biomass pretty well, actually. But with soils, you have a large pool that's variable in space.
Highly variable, yeah.
And then measuring the change. So anytime you cut a forest, you change the temperature of the soil, you change the moisture content, and then you change the inputs and outputs. And to me, that seems the most challenging heart of carbon accounting in any land use.
Mm-hmm.
And, you know, we know a lot about those processes, but they vary among soil types, among textures, among mineralogy, among the types of.
And even within that, you know, if a tree
Yeah.
died 30 years ago at a spot or something, you know, it's going to have a higher carbon stock than 10
Right.
meters away.
So this isn't a criticism at all, it's just like, how do you account for that when you're trying to do carbon counting?
Well,
Yeah.
Yeah, well, a highly variable pool creates a problem, but you're still doing the same thing. You know, you're still going to try and come up with your mean, and you may have a lower precision, so you may have a wider range about that, but you're still trying to come up with that numbers. The problem we've had, you know, back a while, we were working a lot with utility companies doing tree planting in the US back when they were pretty sure they were going to be capped and would have to do something, and so we'd set up these plots. A lot of them were in bottomland forest across the south. And you know, we could put in and measure those trees every so many years, but you would have to have a longer time period for the soil. You'd only be able to come back every 10 years or every 15 years or every 20 years, because you would have time 1 carbon stock plus or minus a bunch, and time 2 carbon stock plus or minus a bunch. And therefore, to be very confident that you actually have a gain, you have to deal with the uncertainty on both ends. And it's a problem. We do rely on the IPCC a decent amount, particularly in the tropics, and the IPCC sets up all these relationships, and they're certainly going to be significantly plus or minus. But they typically assume that you know, there's a certain proportion of the soil carbon is lost after deforestation based on the subpart post-deforestation land use, and that loss happens over a 20-year period. So we do have to operate on a bunch of assumptions that are based on the literature, on science that's been done for a long time, and a couple of scientists who are stuck on the IPCC's panel and have their opinions. But you know, those are the approaches we have to deal with. We have to deal with the uncertainty. We have to deal with the variation and try and find solutions that doesn't just make us throw our hands up and give up, right? We have to be pragmatic on some of these things. And the peat soils are they're some of the real one, right? And mangrove soils to a big extent as well. You can have just massive stores there, like dwarfing the stores in the trees. And there's so much that is hard to know. With the peat, you have to know rate at which drainage is happening, what drainage happened in the past, you know, what the stock's there, what's the balance of different greenhouse gases, what's the balance of methane against nitrous oxide. You know, having I had these discussions about prairie potholes, some of you may know up in the Midwest, and the possibility of having a carbon project in those based on potentially restoring some prairie potholes. But that just creates a whole can of worms, right? If you have a dried out system, yes, a bunch of emissions happened in the past, but if you suddenly come in and re-wet that system, then suddenly you're starting an awful lot of emissions that are going to happen forever on that wetland in order to achieve a certain degree of carbon sequestration. And sometimes the sums don't work out on these things at all. I was talking to John before as well about fire, and we had this big push and a big idea that treating forests against fire would be a great way to reduce greenhouse gases. That California and most of the West Coast, most of their land use emissions are from those forest fires, and it's something that's picking up all the time. We've had well over a century now of fire suppression, and because of that we have these forests that are full of fuels that are ready to burn. The idea was you could come in, you could thin it out and take some of that biomass out, and therefore a fire that came through potentially would just burn through the understory and have very few emissions. The problem is that if you have a system whereby the fire's coming through every 2 or 3 years, that won't be a forest at all. Forest can't survive that. These high fire prone forests are still having a fire every 100 or 120 years. And so if you treat every single hectare, you are causing a whole lot of emissions that you can't even save in terms of the fire, because the fire is too infrequent. So, you know, there's a lot of thorny issues when you get into this calculating, and a lot of them are anthropogenic. You know, we've created problems for ourselves that are very hard to get out of.
Can I just suggest a way out of the woods?
Go on.
So one of the things, and you're aware of these flux towers, I think. So one of the ways to sort of indirectly measure carbon change in soil is to use at Ecovariance
Mhm.
tower, which is a tower that has a sonic anemometer that measures the at a very high frequency, the direction and speed of air, and then also measures CO2 with a gas analyzer. And I guess you could do it with N2O and methane too, with some kind of fancy laser. But you can take a whole system and you can look at the net flux across a year. If you do biometrics, allometrics,
Mhm.
on your pre and post harvested trees, you can account for that carbon loss. And then you can take the net flux from the atmosphere to the biosphere, whichever way it goes,
Mhm.
and essentially get a pretty robust estimate of how much is either gained or lost from carbon. And it seems to me, and I do this in a network in temperate forests, which are regrowing, and so I don't know if there are any of these flux towers that are in, recently disturbed or experimentally managed.
There are.
But it seems like those would be great data to inform models
Mhm.
that could actually predict changes in soil carbon
Yeah.
without having to do massive measurements.
Yeah, I mean, I think they are good data. Necessarily they always come up with problems because they have to be an area that's accessible. And how are you disturbing that area by putting the towers in? And what's your, your annual cost and your footprint of your towers? But yeah, absolutely great data. And
Yeah.
good way to, we just need to build up as much of this as possible to try and understand it as well as possible.
Yeah.
How credible are your metrics to other scientists in Cambodia, politicians in Cambodia, farmers in Cambodia? I mean, who accepts these and feels that they are accurate enough or been tested enough or are somehow politically correct enough that it can be used to change land use?
Yeah, it's a really good question, and it's a highly complex question. I don't think I said it, but I often frame my group and what we do is that we translate science, that we sit somewhere between pure academics and policymakers and commodity producers and try and take the science and put it in a form in which it's more easily understood and used. And so, that's typically what we're doing, and we rely heavily on things like the IPCC and other sources that are largely above, not above criticism, but are accepted. So predominantly when we talk to people, we invariably have credibility, and for better or worse, you come into a country as a scientist and you come with some credibility just by doing that. And the fact that I've published, for example, on the logging method or on the degradation numbers, just having peer-reviewed publication within the sector definitely elevates you, because there's an awful lot of people out there writing white papers that no one really looks at and therefore runs into credibility. So there are a number of different layers to that. Typically what we say is believed and accepted. Within many of these countries, there's a lot of, necessarily and correctly, there's a lot of pride. And so they often want their own data and they want their own processes. So it is important when we work in countries that we work very closely with the governments and have them have some ownership. Because without that, they're like, okay, this is something else from the US and I'm just going to ignore it and it's going to sit in their filing cabinet. So it's something that you really have to think about from the beginning to the end. And we've made mistakes in the past where we've gone and spent a bunch of money and it's achieved absolutely nothing because you haven't framed it right and you haven't put it in the right place to be used. But if you go through those steps, and the West tool, for example, is a good example of that. My colleagues work very closely with the Cambodian government, with the local administration units, and it's reached the point where they really want to accept it and they want to use it broadly because they believe in it, and they believe it's something that they can have ownership of.
Can they have successful tests? I mean, successful outcome or unsuccessful outcome based upon what they've done. I mean, the water table or something, some other metric which would be economically valuable to them. I mean, can they test can they verify that the models are useful?
In theory, the challenge really is that you need a broad-scale impact to be able to pick up at the other end the response. We work in payment performance in the US, for example, where we're working with farmers and we model on a particular farm. You change your practice. You put in cover crops. You put in buffers along the rivers, and you are going to achieve, X units of reduction in nitrate offlow or phosphate offlow or something. But the ability to then go ahead and pick that up in the watershed is almost nil unless you suddenly get 60 or 70% or 80% of the farmers participating to have a direct effect. So we run into this constant problem in terms of small scale impact on big scale problem. And so the same would happen with a number of these Cambodian issues, that what we have is a 30,000 foot model really coming in, and if someone wants to use that and get an answer in their square meter, they're going to run into serious problems. So there are two levels to that. One, the concepts, the theory, the impacts, all of those are genuine. The specific number is going to have an imprecision that's plus or minus, and when you start working with farms, for example, then you're going to move to doing a precise model. You're going to do a SWOT model or something like that specifically on that area, and therefore get a much more precise number, which isn't. The Cambodia model, for example, was modeled the whole Mekong Basin, which is a massive, massive area. So you would be challenged to verify a number from a specific farm based on that. And so, for better or worse, I think, ideally, yes, you'd want to go in and demonstrate in many places that it's exactly right, but the design of it, the scale of it, acts against that a little bit.
I want to ask a bit about the extent you've looked at I've heard that essentially sink enhancement, but sort of what's going on. I mean, I understand that in a number of big northern temperate zones, as you have the out-migration from rural areas and the intensification of agriculture, we have some forests just kind of coming back. Here, some parts of North America, even some parts of China. Have you guys examined any of that and tried to do more detailed characterization? I know the Global Carbon Project literature really is just kind of trying to guess at that at a very broad level. Have you done that, and are the tools applicable to that if one were to try to do that to get a better characterization on that?
Yeah, I mean, we really haven't. The US scale thing is something that was happening a couple of years ago, more so than is happening now.
Well,
I think.
right, yeah.
And then China is not something we've been able to work in a great detail. We're working with countries, for example, Costa Rica, who have this big aim to be carbon neutral by 2020. They want to achieve that, and they have some forest recovery, and we're helping them think about that. But no, we've never done any modeling that's looking at We do very little. We work with sociologists, but we don't do the sociology ourselves. So we don't have any modeling of movement of peoples and then trying to connect that with forest restoration. But I mean, it's definitely a fascinating area, and hopefully going to be increasingly so. We should start to see that in countries as they're developing, and Southeast Asia, for example, is going to be a good example of that. We've just had massive forest loss, and is there potential for that to come back?
Mm-hmm.
Some of that is the reforestation specifically for greenhouse gases, and some of it hopefully is something we're just going to benefit because of demographic change.
Right, and I was getting at essentially, it sounds like people are not looking at it yet, but to actually then characterize what's coming back, because it's coming back in a changed climate. I mean, it's already been.
Yeah.
What comes back and what is the actual strength of that sink locally.
Will be really interesting. I think we can say that most countries it's certainly not happening yet. China is certainly, but countries like China, in most places the pressure on the forest is massive.
Sure.
You're not getting unused land existing in most countries currently.
I had two questions, one rather specific and one a little bit off the wall too. You showed, for example, the West tool and a couple of these tools and gave as an example Cambodia. What's the geographic reach of these kinds of tools? How broadly have you applied them? You showed, for example, at the very beginning where you operate globally, I think in light blue. Obviously, you probably haven't applied and done all the research or the data collection to be able to apply a West tool across all those regions. How broadly have you been able to do that?
Yeah, so it depends on the tool. So some of the greenhouse gas tools we can do globally because we're building off data sets we have that apply globally. When you get into water, you're severely challenged because it does take a hydrological analysis, and that has to be done on a watershed by watershed basis. So it was a massive piece of work to do a water basin as big as the Mekong. It's something that we're talking about doing the same in other places and definitely have interest, but it's a big upfront analysis to do the hydrology, and then we build everything else on top and allow that all to happen. But there's no hydrology big data set yet, unfortunately. Maybe one day there could be, but there isn't right now, and that analysis has to be done on a watershed by watershed basis, looking at the soil types and looking at the amount of dams that are happening on those watersheds. And there's so many different factors that come into affecting what that water's going to do.
So that was sort of a demonstration of the tool, in a sense, doing the Mekong.
Doing the Mekong,
Yep.
exactly.
Okay.
Where there was a demand. We, for better or worse, we're a not-for-profit organization operating on soft money, so the amount of opportunities we have to do something where it's just something we would really like to do is not always there. Usually has to be someone demanding our services.
So the other question that I have, maybe for anybody else in the room, one of the things that I don't know is in entities setting greenhouse gas reduction targets, the baseline year seems to vary a lot. And is there a standard? I mean, I'm working in Ann Arbor, and just in the case of Ann Arbor and our climate action plan in the University of Michigan, the baseline years are 2 different years, even though the 2 entities are intertwined. Is there a standard or an emerging standard?
Under Paris, then people are tending to look at 2020 as
a baseline?
As a starting point. But I mean, it's not really a base. That's sort of the point at which they are going to implement emission reductions. Then the point at which they're saying against which, it really does vary by country. Some countries are saying, this is what our projection would expect under current trajectory by 2030, and we're going to be 30% below that. And then there are other countries that are saying, this is what we had in 2010, and we're going to reduce that by 10% or 20%. So really, there's just a whole lot of politics there.
Okay.
So the answer is there are multiple targets and baselines, but
Yeah.
And that's some of Paris, right? I mean, it really was trying to bring together a lot of different viewpoints and perspectives and try and find something that everyone can agree to.
Obviously, things can be manipulated that way, and also even the scope, whether it's scope 1, 2, 3, different targets can also be made easier or tougher depending on scope definitions. So it's really difficult to look at the surface and understand how do you benchmark one entity against another entity without taking a deeper dive. Yeah. Okay, thanks.
Well done.
Looks like we've,
Try people up.
yeah, well, great. Well, let's give a nice round of applause to Frank. Excellent presentation.
oh,
Yeah. Feel free to linger for cookies and coffee.
Thank you. Dr. Pearson, where do you work? In Arkansas or?
In DC.